A very good morning to all of you. We are just waiting for the chair to join, then we'll begin the session.
Hi, Vipula. Yes, Sanjeev Mehan not there?
No, sir, he has not joined yet.
Okay, don't worry. So we can start this session. I will take over from that side. Okay?
Okay, sir. A very good morning to all of you. You are welcome in the session 19, that's on fashion, fabric, and technology. So to chair the session, we have the eminent scientist Professor Bhuvnesh Gupta from IIT Delhi. He'll be chairing the session today. Over to you, sir.
Okay, thank you, Vipula. Welcome to this session, which is on fashion, fabric, and technology. There are 4 talks, 2 invited talks and 2 oral talks. And the invited talk is for 15 minutes each. The oral talk is for 10 minutes each. So I would like to request all the presenters to please stay within your presentation should be in that time slot, and leave at least a couple of minutes so that there's some discussion on your presentation. And so let us begin with the first talk. This is by Kamaljeet Singh, NIFT Kangra. If she's around.
Sorry to say, no, she's not around. We can move to the second one.
Okay, second also, Shivani said, Srivani said she would like to make presentation at the end. And so, Dr. Srivani, would you like to make presentation now or at the end? How is it?
So she's present here. Ms. Shivani, please unmute yourself.
I think she's not there. She sent a message. She would like to be present at the end. Okay, third one, Chuan Tang.
She's also not present yet.
Not there. The last one, Lin Zing. Not there. Okay, so in this session, you can say session is almost over without any presentation. So if Shivani is there, probably, no, Dr. Shivani, are you around? If you are there, we can go for your presentation. Otherwise, session ends. Okay.
So she's there, but I guess she's not yet in the meeting.
She logged in and probably she has.
Yes, sir. Yes, sir.
So I would request all other delegates of this session, they can join other session because there is absolutely no talk at the moment in the session. The only talk will be there when Shivani is there. Okay. So till then we still like that, and you are free to join other sessions. Thank you.
Thank you, sir.
Hello.
Hello, good morning, sir.
Good morning. I must ask you to excuse me because I had a very late night yesterday. I was not well, and my everything was actually rather haywire. And can we start the session now?
Yes, sir. So actually, there was no participant present, but we can start it because one of the speaker has joined yet. So very warm welcome to you, to all the participants in the session 19. That's on fashion, fabric, and technology. First of all, I would like an opportunity to introduce Mr. Sanjeev Mehan. He's a co-founder and chief executive officer at ICL Digital Private Limited. I welcome you, sir. Sir,
And my apologies once again, sincere to everyone.
Sir, we have a new speaker added in the session. This is Dr. Harun.
Yeah.
So you have to introduce him to the session.
Yeah. Okay. Wait a sec. Listen, before I have to get my bearings right, so would you be kind enough to just introduce him for the moment? I have to get my bearings right. Right.
Okay.
So just say a few words about him, please, for the moment. I just need to get my. So I'll just
maybe I can just say about myself. So myself Harun Venkatesan. I have joined as assistant professor in Institute of Technology, Delhi. This is a talk about spider silks. I would like to share my slides. One moment. Yeah, my session was supposed to yesterday. Unfortunately, I could not join. So this might be. Very good morning, everyone. Thank you, Professor Bhunesh Gupta, as well as thank you, the panel members, for giving this opportunity to present my topic. So today I will be presenting on artificial spider-web, a versatile biopolymer for smart materials. So the basic content of my presentation is classified into 5 sections, starting with introduction and what are the ways that artificial spider silk can be produced, followed by smart properties of spider silks and my research outcomes, and what might be the challenges and future perspectives regarding the artificial spider production. So spider silk is well known as a natural fiber, and it is lightweight as well as has high toughness. And one of the interesting properties of the spider silk is like excellent compatibility and low immunogenicity as well. And normally it was used by ancient Greeks to heal bleeding wounds. And later on, this spider silk in the early part of the 19th century, it started gaining a lot of attention because of its enormous strength and other interesting properties as well. So a brief comparison of the properties of spider silk in compared to other fibers are given in this table. So almost spider silk tops here with the strength of 4 gigapascal and elongation of about 35 percentage. So why the both high strength and its elongation make it very tough as well. So that becomes one of the most highlighted properties of spider silk. So here almost the 4 gigapascal is attained by one of the spider called bark spider. So it can build huge nest, like even the nest can cross between the streams and lakes sometimes. So these kind of spiders were able to produce a dragline silk about 4 gigapascal strength. So the fascinating properties have gathered interest of a lot of scientists, and they wanted to mimic this kind of fibers. But however, unlike silkworms, these spiders cannot be formed. So we have to find some new methods how we to extract such fibers. And for that, biotechnological approaches became one of the prominent thing, where they used recombinant technology to produce spider proteins and make fibers out of it. So how the the design of the spider silk actually is done like by nature is we have three components that work synergistically to produce a fiber with certain properties. The first one is the structure. The structure here refers to the primary, secondary, tertiary, and quaternary structure of protein that actually determines the final properties of the fiber, and a particular process, the fiber spinning process, that is actually adapted by the spider. So not the spider produces multiple fibers, and the production process of each fibers are not the same. It means like the spider applies different tension for producing different fiber, and different tension in the sense that we produce a different shear and elongation in the spinning duct of the spider spigot. And based on that, and also the type of gland and whatever the different amino acid composition of the spideroin being produced, so that decides the final properties of the fiber and where that particular fiber will be used by the spider. So the natural properties of protein fibers in general, they start from this unit structure, which is the chemical background or a primary structure, followed by the macromolecular structure and the supramolecular structure, where we will form the final crystals and the spring-like random coils or amorphous regions that actually responds to the final properties of the fiber. So here, the main amino acids that is present in natural protein fibers or any spider silks or alanine, cysteine, and glycine. So it and its composition varies in different protein fibers. Whereas the response, like in crystal formation and structural stability, it plays a main role. And low weight percentage in soybean fiber and casein is around 2%, especially this alanine. Cysteine and glycine that produces very weak fibers in general. So for getting better strength and better mechanical properties, we need alanine and glycine at higher concentrations, and that will enable in the production of a dimensionally stable protein fiber. And that makes silk or spider silks very attractive. So these kind of proteins can have such high amounts of glycine and alanine, and that enables the spider for producing different types of silks for its different use. So yeah, normal spider can produce 8 different types of silks. It starts from major ampullate, minor ampullate, flagelliform, tubuliform, aciniform, piriform, and aggregate, and each have its own application as shown in the figure. So let's say like a tubuliform silk will be used to protect the spider eggs, and a dragline silk is a typical silk which has the highest strength, is used by the spider to hang when it is moving. And there is a aciniform silk for used for prey wrapping, which is also shown here. And also like flagelliform silk for prey capture. It is actually in the form of spirals in the web frame. And yeah, these are the multiple silks. Like, what is the difference is the key amino acid motifs. Like each silk have its own repetitive arrangement and kind of amino acids because they are produced by different glands, and that makes the spider a smart being as well for producing multiple different fibers from its own from a single body. So that is the very important point. And not only they are different, they have different mechanical properties tailored for its particular usage. So that is shown here. So the major ampullate silk is one of the strongest silk because it has very strong property, and minor ampullate silk sometimes they are even stronger in one of other species of silks. And aciniform silk is given here, they have higher extensibility. And also flagelliform silks, they are like almost behave like a rubber. So you can see it is mentioned as W, and cylindriform silk is used for wrapping the prey. So they have a variable mechanical property. The basic difference between spider silk and silkworm silk is their arrangement of amino acids. Silkworm silk is rich with randomly arranged amino acids with the glycine and alanine, whereas spider silk has a perfectly repeating alanine and glycine rich regions, and that makes yields the production of very aligned anti-parallel beta sheets in this structure that finally contributes to the final mechanical properties of the fiber. And this is a basic comparison given here. And the history of spider silk making has been has been so long, but however, the initiation of artificial protein based fiber production have started in around 1940s. So how that even though there was lot of attempts, it was found that the poor elasticity, low width strength, bad thermal stability, low moisture regain, and alloying problem are some of the issues, and that has actually deteriorated the interest in artificial spider silk in the early 19th century. But however, the start of research in spider silk, especially on recombinant spider silk, have started to overcome those problems in recent days. And the current application of spider silk can be broadly divided into two areas. First one is the biomedical. So we can be able to use spider proteins in different forms through spinning, through salting out to form microspheres and to form certain self-assembled structures as well as films. So they can be used in artificial nerve construct, the drug delivery systems, scaffolds, and implant coating as well. So these are the wide range of applications. And in high performance nowadays, a lot of companies have started producing spider silk based products. So one such is sports shoes from Adidas was produced from blue protein, and a body armor from Craig Labs. They are using spider silk for developing body armors, spider silk, artificial spider silk for producing body armors. And one of the moon parka developed by North Face is made of blue protein from based on spider silk structure and bolt threads. Where they have actually produced a tie out of it using the blue protein as well. So the recombinant technology that is employed for preparing spider silk utilizes the DNA, where we use the spider DNA and transfer it to a new host, and that host will be able to translate the DNA and transform it to protein. And popularly used the expression systems are microbes, cells, and transgenic animals and transgenic plants. Um, However, these transgenic animals are kind of quite expensive, and they are not providing a lot of yield. So the most popular expression systems nowadays are like microbe based, as well as in the transgenic animals. Like here I have included Bombyx mori, so we can even express the protein through silkworm. So we will be able to produce the fiber directly. And so this is the current state of research, where a different expression system has compared, and bacteria and insect based system like Bombyx mori were able to produce native size spidroin of around 200 and 280 and 300 kilodalton. So the native production of native size spidroin becomes very important in case of better strength and just try to match the properties of the actual spider silk. So here we have to so a lot of research has been done to achieve such high level, because in normal it is very difficult to express such high molecular weight protein in any host system. So spider protein from bacterial host was one of my area, like where I used all these processes, right from gene codon selection to gene expression, to produce the spider protein using the fermentation process. And here we used to construct the spider protein from obtaining the gene coding from the gene bank, and we will be translating the gene coding into synthetic plasmid and transforming that plasmid into a bacteria to express the protein. So that is presented here. And also we were having some ongoing research to produce silkworm based spider silk. So we were able to infuse a new gene into a piggyback vector and try to microinject it. This work is currently on progress right now. And this is the simple mechanism of protein expression is given here. Like we are transferring the DNA of the spiroid from the gene bank, and this DNA acts as workhorses that actually has the code for expressing the protein. In the first step, the information the DNA is transferred to the messenger RNA with the help of an enzyme called RNA polymerase through a process called transcription. And followed by that is the translation of such mRNA messages to a protein, and we will be able to produce such protein with the help of the ribosome. So it is this depicted here to this picture. Oh, sorry, my slides are stuck. I have to restart the program.
Please go ahead.
Sorry, 1 minute. My slides are stuck. I'm sorry.
Please go ahead.
Sorry, my slides are stuck. It's restarting right now. 1 minute.
Sure.
Yeah.
Take your time, Dr. Arun.
Sure. Yep. There's supposed to video to be run, but it's not running. I don't know. Yeah. The smart properties of spider silk are wide, as there are many smart properties. So I have listed few of them. So super contraction is one of them, and the spider silk having torsional memory, where it can actually can rotate back to its original position, even like how even after number of twisting, and it will be able to collect water from the atmosphere as well, and it can conduct phonons as well, to like it is depicted in the acoustic properties, as well as it will be able to transmit light through its fiber. So these are some of the smart properties that are being highlighted and evenly and also widely researched in
So
recent
sorry to
years.
interrupt you. We can't see
Yeah.
your slides.
Oh, is it? One minute. Is it okay?
Yeah, they are visible now.
Yeah. So I was talking about the different smart properties: super contraction, torsional memory, water collection, optical properties, and acoustic properties. Like these are the smart properties are actually there for spider silk. There are people are even discovering some new additional, but I don't want to go into deep. But these are the 5 main properties that are being highlighted, even when published in a lot of leading journals like Nature, Advanced Materials, and even Science, etc. So I don't know what is happening after this slide. I'm not able to change it.
So maybe you can select the next slide and start share screen.
Yeah. I will do that. I will do that. Yes. That's some technical glitch. I even don't understand. It doesn't happen, but I will just start with the next slides. Right. Yeah, and talking about the super contraction, Supercontraction is one of the most highlighted properties, like where the spider silk were able to shrink up to 70% when exposed to higher humidity, like in this range. And this is happening because of the association and dissociation of hydrogen bonding present in the highly entropic structure, like when we can stretch it and fix it to a particular position, and when it is exposed to higher humidity, and we will be able to recover the original shape. And this particular fiber, when held in restrained conditions, will generate stress as well. So that makes supercontraction a very important phenomena. And also supercontraction is one such thing that the spider web undergoes during every day, because it will be impacted by a lot of insects as well as birds, and that actually pulls the fiber and elongates it to greater extent. Then when exposed to the dew in the early morning, and this fiber super contract to its original position, and helps in recovery of the web. So this is the main function of the super contracting fiber. And another example is a water collection. So water collection here, where the fiber has some special spindle knot structure, and this spindle knot structure will have nanofiber like arrangement like this. And this nanofiber consists of hydrophilic amino acids, especially which can attract the atmospheric dew, and as well as atmospheric fog or whatever it is, and that can condense these in the form of large drops, and that can be used in the recovery of the web that is actually deformed. And even these drops act as a source of water for the spider to consume as well. So this is one of an example. And there is the thermal behavior and sound transport. One of the most highlighting part of the spider silk is having like, because of its very highly aligned beta sheet structure, there is the spider silk can produce a very high amount of thermal conductivity, which is 416 watt per meter Kelvin. So that is one of the highest among natural fibers, and even close to that of metals as well. So that makes this fiber one of the one unique material that even this kind of highly aligned crystal structure also allows the transport of phonons. So it means it will be able to transport even a very a low frequency sound so the spider can know that something is happening around it environment. So these are the higher main properties. And this work that I will be showing will be based on spider dragnet silk. So how we extracted the spider protein from Escherichia coli, as well as producing a capture silk like fiber, where we're able to harvest water from atmosphere, and you use the silkworm silk coated with spider silk protein to achieve these properties. And the first one will be based on supercontraction, where the fiber was able to shrink around 70% when exposed to humidity. And this is kind of a smart shape memory behavior, because the crystalline region acts as a net point, and the amorphous region acts as a malleable switch point. So this kind of structure, from this we will be able to achieve a shape memory effect. The shape memory effect is nothing but the capability of a material to recover its permanent shape from a deformed or a temporary shape is the shape memory property. And the amorphous region comprising of alpha helix, beta turn, and random coil would be responsible for fixing the temporary shape and triggering shape memory by disruption of hydrogen bonding when exposed to higher humidity levels. So this is a typical sequence that we employed in expressing our protein in E. coli. So it is a chimeric protein where we used MASP1 protein from E. australis spider, and MISP, which is a minor ampulate spiderine from Aranus ventricosus. So we engineered a sequence called EMASP2 with terminal regions from two different spiders as well. So the theoretical molecular weight was around 33, which is actually 1/10 of the actual molecular weight of the spideroid. And we used 335 amino acids to produce this protein. And this agrosgel separation shows a target DNA around 1 kb was developed, and it is transferred to expression vector. Expression vector is used for expressing protein in E. coli. Actually, and this is the confirmation of a protein molecular weight that we have expressed. So the protein molecular weight is around 32 kDa. You can see it here through SDS page gel test, and we also confirmed the molecular weight through dynamic night scattering. So we will be able to achieve around a theoretical molecular weight of 60 kDa due to the dimerization of C-terminal and N-terminal regions at pH 8. And a typical fiber formation process employs two different theories, but however, still there is confusion, which is the correct theory. But the theories include liquid crystal theory and missile theory. In liquid crystal theory, normally we use the spiroids form dimers and aligns itself to form crystal-like structures or temporary beta sheet structures. So that actually when we apply shear, it will be able to convert to fiber by the removal of water through the spider spinning duct. And missile theory shows that dimerization occurs within the length of the spiroid protein itself, and this spiroid protein will form missils such like this. And when applied shear and stress, we will be able to produce fiber when the protein process through this particular spinning duct. And this is our research work. So we were able to produce a biomimetic spinning through engineering the spider protein, and this particular NNC terminal region we have used, we are able to produce spiders using biomimetic spinning, because traditionally a very strong alcohols have been used to denature the protein, whereas we employed just salt-based solutions to spin these fibers actually. And these are the fibers that are spun at different pH concentration of the salts, and we were able to produce fibrillar structure as shown here, as well as a nanoglobular structure similar to the natural spiroid. And so one of the benefits of our molecular design is we were able to produce the spider through a lock and trigger mechanism through ionic interaction without using organic solvents that actually dehydrates the fiber and makes the fiber very hydrophobic. And using this fiber, making the fiber hydrophilic is very, very important because we are able to achieve good super contraction, so the water can be absorbed more. And this is the secondary structure confirmation of the spider protein that we have expressed. The spider silk protein was having excellent like representation similar to that of natural spider silk as well. Now, so that we are compared the natural spider, we got this spider for silk from the forest, and then we compared that with our actual protein, and they almost have a similar resemblance. And even our material had a higher beta turn, which is very, very important for the super contraction. Beta turn is nothing but a spring-like arrangement that enhances the recovery of the protein fiber when exposed to higher humidity. So this is an example how the spider silk protein fiber was able to recover its original shape when exposed to higher humidity. So this is the programming sequence, and we were able to produce a very high recovery stress around 20 megapascal, which is even like higher compared to a lot of polymeric fibers as well. So this is mainly attributed to the molecular structure of the spider protein, and also the shape memory cycle was tested. We were able to achieve a shape memory ratio of around 98% even after 5 different cycles of shape memory testing. And these are the mechanical performance. The maximum strength that we achieved was around 169 plus or minus 9, and this is almost 1/10 of the actual the natural spider fiber, because we also produced 1/10 of molecular weight, so it resembles the molecular weight proportionately as well. And we also did a molecular dynamic simulation, testing of hydrogen bonding. Like here, we were able to find a very interesting thing. Even the simulation, we achieved a huge difference in hydrogen bonding at exposure of 75% of humidity, and that makes the fiber very important. So this particular range of humidity is very important for achieving supercontraction. And there is, of course, a change interaction of water molecules being in influencing the amorphous and crystalline region was also studied, and contraction percentage was compared as well. So increasing the amount of humidity was increasing the contraction percentage, as well as it has some change in the molecular structure length as well. So the water molecules distribution at 75% hydration is also highlighted here. So this is how the water molecules collect in between the amorphous and crystalline regions to enable the fiber to contract at higher humidity levels. And this is the different stage of exposure at different levels of humidity, and the contraction happens at higher humidity levels is shown here. And our next work was for producing artificial capture silk fiber with the extremely high volume directional water collection. It's like this is mimicking the like dew capturing capacity of the spider silk fibers is highlighted here. So actually the spindle knots that is actually present in the spider silk give rise to a surface energy gradient, and also produce a difference in Laplace pressure that allows the dews that is absorbed by the fiber at higher humidity levels to coalesce to form droplets. So these are the concepts behind the coalescence process, and that enables a directional collection of water towards the spindle knot when exposed to higher humidity levels. And our work is to exploit the properties of silkworm. So even silkworm had natural unevenness when silkworm silk had natural unevenness. So we try to utilize its benefits to produce and mimic the natural properties of the silk. And we used EMSP2 spider which was expressed previously, and we did coating process. And that particular coating process produced a spindle knot like structure similar to that of natural one because of the Rayleigh splitting. Rayleigh splitting is nothing but due to the high surface tension of the water or any solvent or kind of material being applied, it will be split in smaller droplets with lesser surface energy because of the high surface energy tension. So we were able to produce such structures here. And these structures are also highlighted where having dimensions are shown here. And that particular structure enabled us to collect water from the atmosphere and to produce droplets like this. And these droplets can be used for different, like this kind of concept can be applied in areas where we want to harvest water in like especially a water scarce region or something. So these were our target applications, and our fiber was able to produce 100 times higher water collection efficiency in terms of volume to mass index compared to previous work that has been published, and as well as we were able to achieve 250 times lighter fibers compared to these existing materials that was previously reported. And this work was highlighted, and also we filed a US patent out of it. And yeah, now we are going to finish up the presentation, like what are the current status of artificial spider silk development. So the silk as shown here, we are somewhere still lagging, we are yet to reach the high performance levels of natural dragline silk. But however, we are able to achieve almost like 50% of the original properties, and lot of methods are being employed, and wet spinning is one of the popular methods where we convert the protein produced using the brew technique or fermentation technique. So we can convert this protein into fibers through wet spinning. And recently, because of the extensive operations involved in
may I intervene, Dr. Harun?
Yes.
The time is short. You have to wind up.
Yeah. Just I have three slides.
Please.
That's it. I'm going to finish. This is the current situation, like where silkworms are used to express a very high molecular weight protein at a very that can produce high strength as well, around 1.2 GPa. This is the latest achievement. And the most important challenges are the spider supply. The natural spinning process plays a major role, because not only the spider is responsible for excellent properties. So we have to produce a spinning system which has the ability of natural spinning of spider silk. And hierarchical structure, super contraction are very important. So because super contraction or is not desirable in normal apparel, so we should make the fiber resistant to water as well. And so application wise, there are a lot of possibilities in biomedicals, fiber optics, electronics, and high performance and etc. So still we are able to achieve the golden standards of silkworm silk, but still spider silk have its own benefits and kind of ability to even replace synthetic nylons and polyester due to its flexibility and more eco-friendly nature. And so currently there are a few companies, like only few companies in the world are working in production of artificial spider silk. Some of them are Bold Threads, Spiber, AM Silk, and Craig Biocraft. So these are some companies. So till 2020, there were around 3,200 publications in this area. And USA, UK, Japan, and China are leading research countries in producing artificial spider silk. And this is the end of my presentation. Thank you.
Thank you very much, Dr. Harun. Dr. Harun spoke about this new, unique extrusion method of,
Yes.
with much better, higher results, for which, he is applied for a patent also. And so this is about spider silk, which is an alternate to silkworm, and it has much higher smart textile properties. So with this, we will like to, any questions, please? Would anyone like to ask any questions?
No, I think the only question, good morning.
Good morning.
I was just wondering about the techno-commercial aspect of this particular project.
Okay.
Yeah, what would be the financial scale on which this particular project would have to be taken up, and what volumes would one break even?
Break even, I'm not sure, because it requires very difficult calculations, and it is not an easy project to carry out, because the companies that I have showed, they're almost $1 billion company right now. Means even the Fiber Inc., which is in Japan, they have been funded heavily, around 5 billion to 10 billion US dollars. It is a very high valued company, because this is in the initial stages, just like polyester and nylon manufacture, which was happening in the early 19th centuries. Like it was being talked a lot in the middle of 19th century. So there have been a lot of funding in those projects as well. So similar to that, there is a lot of funding, but to that particular products that I have shown, they are very expensive. At TAI cost around $200. You can imagine like what is the production cost would be. So and the parka I have showed that it is around $1,200 US, and even there is a big problem of scalability, as well as the kind of commercializing these products, because of its extreme high price. People are trying to bring the price down by applying new techniques through expressing the protein using silkworms. So in terms of company valuation, I would say it is $1 billion like company if you really want to start up something like this. So this is my opinion.
Thank you, Dr. Harun. Please pardon me for asking that particular question, but being from the industry side, that is one of the primary concerns of all the industrialists who would be interested in this.
Yes. I completely understand.
Yeah, but another question, if we have the time, Mr. Mehan, do we
Yeah,
have
sure, sure.
time?
Yeah,
We'll
yeah,
have
yeah,
the
we can.
if you can just, we'll probably take last one question.
Okay.
Yeah.
Just one more question. I mean, since these are protein fibers and we can understand and analyze their structure,
Yes.
what are the possibilities of mimicking it at a much larger scale in plants?
In plants,
Yeah.
people have already tried that. Actually, they were not very successful mimicking that in plants, but
Okay.
they found because the protein is of very high molecular weight, around 300 kilodalton. It is not easy to express that protein in any organism, and that is why even producing that in E. coli becomes so difficult. Like you need a super organism to produce it basically. But for that, there are two different companies, like where one company is using yeast as their main organism, other company is using E. coli as their main organism, and the most successful company was Craig Biocraft. They were able to use CRISPR technology, which is the most advanced gene editing technology right now. Even that technology can be applied for changing the human genes, so that they use that technology to express the protein in the silkworm. So this silkworm can be like bred just like our normal silkworm, and that makes this process very scalable. And only one company has the technology, and that is heavily funded by US military right now. And right now they are about to start their industry in Vietnam. So if you can find some information like through this link, you will get more idea about this particular project. So it is possible. People are still doing it. I think within 10 years we will be achieving a very high maturity of this technology.
Okay. Thank you,
Yes.
Dr. Arun.
Yeah, thank you.
That was an excellent presentation and an eye-opener.
Yeah, thank you. Thank you very much.
Thank
Yeah,
you.
thank you.
Very much, Mr. Mishra, and thank you once again, Dr. Harun, for this outstanding
Yeah.
presentation. So we'll conclude.
Thank you, Professor. Yeah.
So we are done with all the speakers. So if you give the permission, may I conclude this session, sir?
Please go ahead.
Okay. I would like to thank all the respectful speakers for giving us the presentation, and I would also like to thank the session chair, Mr. Sanjeev Mehan, for being there. Thank you so much, sir.
Thank you very much.
I would also request other speakers. We are done with this session. They can join the other breakout room, as some of the speakers are being there in that session. Once that would over, then we'll move to the next sessions.
Good morning, everyone. So we are waiting for our chair, then we will start the session. So good morning, everyone. I am Pratibha Singh, the coordinator of the session for Textile for Advanced Technology. I would like to welcome Professor Abhijit Majumdar from IIT Delhi to please chair the session. Uh, Over to you, sir. Hello. Professor Abhijit, can we start the session, please?
Hello.
Yes, sir. Yes, sir. Now you're audible.
Yeah, sorry, I was not able to join this particular breakout room. There
Sir.
was some problem. So can we start now?
Yes, sir. Yes, sir. Let's start.
Okay, so good morning. This is session 22 of Textiles for Advanced Technology. And as per the schedule, there are 4 technical papers in this session. So the first paper will be delivered by Govardhana Rao Chilukoti. So I invite him to share his screen and start the presentation.
Thank you, sir. Sir, is my screen is visible, sir?
Yes, it's visible.
Okay. Okay. Good morning to one and all. Myself, Govardhan Rao Chilukoti. So my topic is paper making from leaf fibers, and I have evaluated the mechanical properties of the paper, which is made by the leaf fibers. So about our university, I am from Vignan's Foundation for Science, Technology and Research Institute. I am working as an assistant professor from 2013, which is actually located in Guntur, Andhra Pradesh. So coming to my topic specifically, like I selected a topic related to wealth from waste. So actually we are seeing like many grass fibers or grass plants which are available in the surroundings. So my research area is to extract some kind of leaf fibers and make use of these leaf fibers into the specific application. So I selected this topic in the meanwhile, like sustainability in terms of sustainability. So waste to wealth is the main objective of my research area. So materials specific to this project, I have selected these plant leaves like grass fiber and grass which is selected, and I used to make the fibers. After the extraction of fibers, I used binders, so that is also natural binder, to bind the fibers so that the proper binding will be there between the fibers to make the paper. And I used some small instruments also, like hot air oven and mixer grinder and some plates to make the paper. So coming to the methodology part, I have selected 2 factors for this project. So natural gum. So I varied the percentage of natural gum in 4 levels per 1 gram of fibers. I varied 10% of natural gum to 25%, like 10, 15%, 20%, 25%. And I varied the GSM. So I made different GSMs by these combinations. So to take these factors and levels, total 12 combinations are made. So this is the combinational table which I have prepared for the study. Then this is the whole process for the fiber separation and the paper making process. So you can see here the graphs which I have selected for the extraction of fibers. So simply like the first step I have done is like making these fibers in the wet state itself grinded well. So after grinding, the non-fibrous content which is removed by washing into the normal water, room temperature, at room temperature, so that the non-fibrous content is removed. So the fibers I have segregated. So around the fiber percentage, the yield of the fiber is approximately, I got in the study is like 30%. So 30 to 35% it varied. So depends upon the plant growth and all. So I have got like 30 to 35%. Then after the fibers which are separated after washing, so this was dried in the third step. Then after drying, so which further I have gone for the scouring and bleaching process to remove the natural impurities as well as the natural color. So even after like I used a very less amount of like scouring process. That is, in scouring I have used NaOH at 2%, and even the H2O2 for bleaching also used 3%. So even after that also, it is on trial basis I made it. So even though after the scouring and bleaching process also, the natural color still it was there. So you can see the fifth image after the fiber separation and after the bleaching. So this is the at fourth image, it shows that the after bleaching the fibers are. So these fibers again mixed with the selected binder, that is as well as I mentioned that the natural gum. So varied with the different concentrations, 10%, 15% per gram of fiber it is. So both together mixed, then made into a, like as I told that there will be a small sheet of steel. So on the steel plate, like manually we made a sheet, then it was dried. So after drying, the sample was like, we got the paper. So these are the different samples which I made with selected combinations, which is I mentioned before. So after this, we have made a small trial also, whether it can be printable or not, this paper. So I just simply done the printing also on the paper. So after making the product. So this is the final image, which you can see here, the printed image is shown here on the paper. So specifically some areas were crushed or something. It was like because of unevenness of the paper which is made. So this is a whole process route, how I have made different combinations of paper. Then coming to the analysis part, like I have made analysis of the fiber diameter in the optical microscope with the 10x zoom. And I observed that the fiber diameter is around, it varies from 18 to 39, 40 micrometer. Okay. So these are the microscopical images, image which is the leaf fibers which are extracted. Then these are the samples which I made with the different combinations of different like GSMs, as well as the different concentrations of the natural gum. This is a close look. Then after the paper making, I have measured the fabric, the paper thickness, and so you can see here the paper thickness about like at 100 GSM. You can see with so here I measured with the different concentrations of natural gum. Is there any change in the fabric thickness or not? So most probably the fabric thickness is not changing. That once we vary the per gram fiber, what is the percentage of concentration used? Because once we for 200 GSM, as usual, you can say like per 200 GSM also the based on the fiber weight, the concentration or the amount of natural gum is going to be varied. So it is not showing influencing effect or significant result on the paper thickness. But the GSM varies, the fabric thickness is increasing. That is depends. That is because of the linear density, that the GSM grams per square meter of the paper is changed. So the analysis of variance I measured. So here A is nothing but the percentage of natural gum, and B is fabric, the paper GSM. So here the paper GSM is having a significant result, at 95% concentrated, 95% level, confidence level. Then coming to the second measurement that is conducted on bursting strength of the paper. So you can see here the bursting strength of the paper, which was observed by using the bursting strength tester. So in the bursting strength tester, as per the ASTMD standard method, so cartoon test method was conducted. So because it is a paper, so here the 100 GSM is the breaking strength is varied from approximately 6.2 kg per square centimeter to 7 kg per square centimeter for 100 GSM papers, and 150 GSM papers, which is observed around 7.2 to 8.2. It varies because once we are varying the percentage concentration of the natural gum, so from 10% to 25%, once we are increasing the percentage of natural gum, the bursting strength of the paper is observed that the increasing the strength because of the binding points, more binding points. And even the same observations are got from the for the 200 GSM also. So all three are showing the incremental level only after by increasing the concentration of the natural gum. So this is the main effect plots which are made in software, Minitab software. So that generally here it is not showing any significant effect by changing the natural gum concentration from 10% to 25%, but where in GSM 100 GSM to 200 GSM it is increasing. So it shows that the significant level of GSM is shown here, and the percentage of natural gum is not shown that much significant level, but in our previous graph it shows that there will be a small incremental of bursting strength improvement, but it is not too much higher, but it is showing there will be a small change in the improvement of the bursting strength once we are changing the once we are increasing the natural gum concentration in the making process. So this is about the test methods. So still it is in the process for the testing also. Some more tests I need to conduct in the future. So conclusion part from the above experiment. So I observed that the yield, fiber yield, approximately it is 30 to 35% on weight basis I got, and mean diameter of the fiber extracted was about 30 micrometer, which is measured in optical microscope. And GSM shown in both the cases, like paper thickness as well as the bursting strength, both are showing the significant effect. So in the further studies, this is like a preliminary work which I started. So I have a product that is final product which I made, and it can be it can be utilized like hard cardboards and some ornamental papers and all. So this is one example, and final output it is okay. So it can be printable also, and which is like there are two sides of the paper, like the contact side where the paper is contact with the plate will be very smoother, and outer the top layer will be somehow rougher. So which I have printed is like the smoother side of the paper which I printed. So this is the my uh, observations. This is the product, final product. So thank you, sir.
Okay, thank you for your interesting work. Is there any question from the participant? Maybe we can take up one question. If you have any question regarding the paper that has been presented, please go ahead. Okay, so I have one small query. In your research, you have developed, fabrics, the paper
Papers.
of 3 different GSM.
Yes, sir.
And the thickness is in between 1 millimeter to 2 millimeter.
Yes, sir.
And the fiber
0.62.
diameter you have mentioned around 30 micron.
Yes, sir. Yes, sir.
Yeah. So how can you reduce the thickness of the paper for normal application? Any idea on that?
Sir. Hello. Hello.
Yeah. Sorry, the aircraft. Yeah. Do you have any idea how to go for lower thickness of the paper? Because the kind of thickness that you have mentioned, it may not be suitable for non.
Actually, sir, yes, sir. One observation I made is in making process, what is happening is I have not utilized any compression. Means with compression, it is not made, sir. So means say for example, 2 rollers are there. In between the 2 rollers, we have compressed and hot and so that the wet condition of this material becomes drier, and so paper is made. So this is not happened. Actually, we have not compressed very well. So because of maybe that is the reason, the as you mentioned, sir, that is exactly correct. So the thickness of the paper was more compared to the fiber thickness. Say fiber thickness is 30 micrometer, but the paper thickness is around 0.6, which I made 100 GSM. Hello.
Yeah. Sorry, there was some connectivity problem. I think you have already answered.
Yes, sir. Actually, I have not compressed and made the paper, sir.
Yeah. Okay.
So because of that, the thickness of the 100 GSM was approximately around 0.6. I got 0.6 mm. I got. Okay. So if I have a setup, means it is manual process I made, sir. If I have a setup to compress and make the paper, then the paper thickness may be lower than that.
Okay. Thank you very much.
Thank you, sir. Thank you very much.
You may please unshare your screen now. Okay, the next presenter is Dr. Ankita Srivastava. She is from National Institute of Fashion Technology, Jodhpur, India. And her topic would be development of body armor materials with STF treated Kevlar fabrics. So Ankita, you can go ahead.
Yes, sir. Thank you so much, sir. Today I am going to present a presentation on development of body armor materials with shear thickening treated Kevlar fabrics. So I am from Department Department of Textile Design, National Institute of Fashion Technology, Jodhpur. And this work was conducted during my PhD that was held in IIT Delhi under the guidance of Dr. Abhijit Majumdar and Dr. Bhupen Singh Butola. So coming to the body armor material, there are two types of body armor materials that we have. One is called as the hard armor and another is the soft armor. So coming to the hard armor, these are the rigid and heavy fabric structure, which are usually combined with the steel or ceramic plate insertion also. So these kind of hard body armors protect against the very high velocity projectiles such as the rifles, etc. And this is mainly used for the military officers in the high risk region. Whereas another kind of soft body armor materials are available, which are rather more flexible and lighter in weight, which are made by using the multi-layer woven or laminated fabric structure, which is there to protect against the low velocity projectiles such as the handgun or shotguns. And this is mainly used for the routine wear of police officers and security personnel. So my work is based on the soft body armor materials. So coming to the limitation and requirement in existing soft body armor, it was found that the existing soft body armor materials needs 20 to 40 layers of the fabric, which is makes it very heavy for the long duration usage. And also it makes the structure very inflexible, which is uncomfortable to wear for a longer duration. So the requirement in the existing soft body armor materials are to reduce the weight, to improve the flexibility, and by maintaining the impact energy absorption, or maybe to improve the impact energy absorption also if possible. So taking the same objective, we have applied the shear thickening fluids on the soft body armor materials. There are various approaches, but this was found as one of the major approaches which can increase the impact energy absorption while reducing the weight also. So these shear thickening fluids are basically two-phase concentrated dispersion, where one solid phase is there, which consists of rigid nano particles, while this is there with the liquid phase, which acts as a medium or carrier fluid in which these particles are dispersed. So this is the mechanism of shear thickening fluids. You can see here that these STF, that is the shear thickening fluids, when these are in equilibrium, then all the particles are dispersed in random manner. But while increasing the shear rate, these particles shows decrease in the viscosity, and these forms some layers in the dispersion medium. But after increasing the shear rate after a critical value, some particles used to agglomerate, and these makes the viscosity, this actually increases the viscosity at a critical rate, and then it behaves like a solid structure. So this phenomena can be used in the soft body armor materials because it can actually absorb a good amount of impact energy in the soft body armor materials. So in the earlier studies, it has been found that the STF treatment can improve impact resistance performance of the fabric structure, and less layers can be used to fabricate the body armors, which can improve the flexibility and the comfort level of the wearer. But also it has been observed that the material and process parameters used during the STF application can actually significantly contribute to improve the impact resistance performance, which was not explored yet. So my work was based on this, and I have tried to explore the importance of material and process parameters in my study. The materials were used as Kevlar fabric, and some chemicals were used to form the shear thickening fluid. The silica nanoparticles of average particle size of 116 nanometer was used in this study, whereas polyethylene glycol was used as a medium for making the STF. Along with that, ethanol was also used to reduce the viscosity of the STF so that it can treat on the fabric very well. So coming to the fabric treatment, the STF is prepared with silica nanoparticles and polyethylene glycol, taking the 3 different levels of the STF, that is 50%, 60%, and 70% silica nanoparticles in the PEG. Plus another variation was taken with the ethanol, which is a diluent. Here the ethanol is to solvent is to STF ratio was taken as 3:1, 4:1, and 5:1. Then the homogenizer was used to prepare this STF, and the Kevlar fabric was padded. A padding mangle pressure was also varied to see the effect of the padding pressure on the STF treatment and the impact energy absorption. So 3 levels of padding pressure was taken as 1 bar, 2 bar, and 3 bar. Then the fabric was air dried. Bank design plan was used to see the effect of the 3 different factors, which is the silica concentration, padding pressure, and solvent to STF ratio at 3 different levels. So this is the we have measured the add-on percentage by calculating the add-on weight of the untreated fabric and the treated fabric. Also, the dynamic impact resistance test was done with the in-house facility at IIT Delhi, which is by taking the impact resistance or impact speed of 6 meters per second. So these are the results that we have found with the add-on percentage and impact test. So total 15 samples were prepared, and it was found that for the untreated Kevlar fabric, the impact energy absorption was 25 joules, whereas we have got the best results with the which is of 54 joules. So this is almost more than 100% improvement was there in the impact energy absorption, and that is done on the single layer of the Kevlar fabric. So we have plotted some contour diagram to see the effect of two parameters at a time, and we have got that this is the effect of silica concentration and padding pressure on add-on percentage. So we have found that the add-on percentage increases with increase in silica concentration. So here the silica concentration is increasing the add-on percentage also. While we have found that the padding pressure plays rather insignificant role in influencing this add-on percentage in the given range. Again, the effect of silica concentration and the padding pressure on impact energy was observed, and it was found that impact energy absorption increases with increase in silica concentration also, and with the increase in padding pressure also. So this padding pressure has a significant effect on the impact energy absorption, while it was not very significant with the add-on percentage. So maximum impact energy absorption was found with the 70% silica concentration, which was treated at 3 bar pressure. Again, another study was done, another plot was made with the effect of padding pressure and solvent ratio, and we have found that add-on percentage increases with reduction in the solvent ratio. So the more the amount of STF, it would be good for the add-on percentage. Then the effect of padding pressure and solvent ratio on impact energy was observed, and we have found that the impact energy absorption increases with increase in pressure, while it increases with reduction in the solvent to STF ratio. This is the contour plot with the effect of silica concentration and solvent ratio on add-on percentage, and we have found that the add-on percentage again increases with silica concentration. So in all the graphs, in all the contour plots, the add-on percentage was significantly increasing with increase in silica concentration and by reducing the solvent ratio. While for the impact energy absorption result with silica concentration and solvent ratio, we have found that the impact energy absorption increases with increase in silica concentration and with reduction in solvent ratio. So the maximum impact energy absorption was found with 70% silica concentration and solvent ratio of 3:1. So this is the performance matrix that was prepared to summarize the data, and we have found that while the add-on percentage increases with the high silica concentration and low solvent to STF ratio, but it is maximum at low pressure, low padding pressure. While in the case of impact energy absorption, while this is impact energy is again maximum with high silica concentration and low solvent to STF ratio, but the impact energy actually increases with the high padding pressure. So it can be said that because of the high padding pressure, the distribution of the particles, STF particles on the fabric is very high, and the penetration of these STF particles are also very high, and because of that, the impact energy absorption of these Kevlar fabric becomes high also. The same is also verified
Ankita, you
through
need
the
to finish
STM
in 2
micrograph.
minutes.
Yes, sir. So it was found that that at the lower pressure, the distribution of particles are not very high, and the distribution, though the add-on percentage is high, but its distribution is not very uniform. But with the higher pressure, the silica nanoparticles distribution is very uniform as compared to the lower pressure. So the same data was verified with the weapon test also, which is conducted in TBRL. And here the velocity of the bullet was 165.2 meter per second was kept. And we have found that in comparison to the untreated fabric, the effect of padding pressure is really high. And here the impact energy absorption increases significantly at 2 bar pressure. So this STF treatment actually increases the energy absorption by 80% from untreated to maximum padding pressure. So this is the impact performance of multi-layered Kevlar fabric panels. We have formed a single layer, 2-layered and 3-layered panels also. And we got to know that for the untreated sample, it was 24 joules only, while with the 70% concentration, the 3 layers shows the 220 joules of an impact energy absorption. So it can be said that the strengthening effect of this STF is maintained in the multi-layer panels also. So finally, the untreated fabric and STF treated fabrics were observed and we have found that the failure modes of untreated Kevlar fabrics are here mainly due to the yarn pull-out effect, and that is done on the primary yarns only, which are in the direct contact of the bullet, and secondary yarns do not actually contribute in impact energy absorption. While by observing the STF treated fabric, it was found that the failure modes of STF treated Kevlar fabric is dominated by the yarn breakage of each and every yarn which comes into the contact of bullet, and also the secondary yarns have major contribution in impact energy absorption, so that the dome is also formed here. So we can say that here are two common terms, that is the STF concentration and solvent ratio, which influences the add-on and impact energy absorption in the similar manner, but padding pressure shows the reverse effect on add-on percentage and impact ratio. So hence the higher silica concentration, higher padding pressure, and lower solvent ratio actually felicitates the higher impact energy absorption by the STF treated Kevlar fabric. And effect of padding pressure was also verified by the weapon test, which shows almost 125% increasing ballistic impact energy absorption. So thank you so much.
Okay, thank you, Dr. Ankita, for finishing in time. I think Mr. Shailesh Kaushik has already raised his hand. Please go ahead.
Sir, my question to Dr. Ankita is that there are specified tests to test a bulletproof jacket. Apart from what she has, the test she has undertaken. So has she tested her material on that as per those standards?
Yes, so there are NIJ standards which is followed for the soft body armor material, that is NIJ standard 1. So we have tried to follow the same standard, while the NIJ standard from 2 to 6 is for hard body armor. So we have not tried that one because our aim is for the soft body armor materials.
I mean to say there are standards where you measure the profile, that how deep the penetration is in terms of millimeter, etc. I'm talking about those
Okay,
standards
no,
which
no.
Gandhinagar
That was not
labs.
done during my study.
Sorry?
That was not done during my study.
Okay, but that's quite important because the forces, they measure or benchmark the bulletproof jackets as per their standards only. Thank you.
Okay, thank you very much. Yeah, the question was really important, just to evaluate the backface signature of the armor when it stops the bullet. Is there any other question from the audience? Otherwise,
I
yeah,
have
please go ahead. Harun, please go ahead, Dr. Harun. Please.
Yes. Regarding that dome formation, I just want to know like how this dome is formed.
This dome was formed because the STF was playing as a bridging material between the yarns, and because of that, not only the primary yarn which comes into the contact of the bullet, but also the secondary yarns also plays actually that for the impact energy absorption of the whole material. And because of that, the dome was created after the bulletproof test.
Okay, you have coated your material with STF, shear thickening fluid, right? So
Yes.
STF normally works well when it is in liquid form. Like when you are drying it, how it differs, the properties and other things, because there is no liquid for it to kind of really do its mechanism of action, right? Like how it is possible to achieve this.
Actually, we have done the rheological test also for all the dried samples, and there we got to know that the rheological properties are showing the shear thickening effect on the fabric.
So how you were able to do rheological test on the dried fabric in general? Like
this is done. What?
Means how you are able to do the rheological test of the dried fabric, I'm asking.
No, that was not done on the fabric. That was done for the STF only.
STF powder?
Shear thickening fluid that was made. Yes.
I see. Okay, and when you're padding this STF onto the fabric, like you told, like you are applying higher pressure or something. So this kind of pressure points also will create kind of some processing difficulties, right? Because you are applying the shear thickening fluid, and between the nips definitely there will be some kind of high pressure and shear region, right? So whether it affected your processing in like padding this fabric with STFs?
Sorry, can you please ask again?
Because when you're padding this STF fluid, so there will be shear forces in between the padding rollers as well. Like there will be a lot of pressure and shear between the fabric and the padding mangle. So how you really control this process, because this shear thickening will have some effect. Maybe even it can stop the mission in this case if you are running it fast. Did you find any
So
problem?
because of that only, yes. So because of that only, we have used the ethanol also to reduce the viscosity, and so that it can actually the fabric can be treated well with the STF. So we have used the ethanol during the padding, and after the drying of the fabric in the hot air oven, the ethanol was evaporated. So there was no role of ethanol for the impact energy absorption, but that was there just to make sure that the fabric is treated well with the STF.
Okay, thank you. That's my questions.
Thank you.
Professor, I have asked my question. Yes.
Sir, you're not audible. Professor Abhijit.
Yeah. Thank you, Dr. Harun, for asking the questions. And Dr. Ankita, thank you very much for your nice presentation. Now we'll move to the next presentation, which will be delivered by Swati Chaudhary from VJTI, and the topic would be evaluation of thermal insulation properties of recycled polyester and cap of multilayer non-woven for outdoor mushroom cultivation. Over to Dr. Swati. Yeah, make it full screen.
Hello. Hello.
Yeah, please go ahead. Please go ahead. You can.
Yes, sir. Yes. Myself Swati Chaudhary from VJTI, sir. My study is on evaluation of thermal insulation properties of recycled polyester and capoc multilayer non-woven for the outdoor mushroom cultivation. The mushroom farming is one of the most profitable agri-business, giving higher net income with low investment and space. And India, button mushroom and oyster mushroom is farming generally happens in hilly regions due to the cold environment, low temperature and high humidity. But as the demand is increasing in of mushroom, it is now adopted also in adjoining states like Punjab and Rajasthan, where the technological interventions in mushroom house is required. Climate of this state is categorized as hot and semi-arid temperature, and desired for button mushroom farming is available in hot and semi-arid region from December to February only. And during that only one crop is possible because we require the temperature at 14 to 18 degrees Celsius. However, after March, ambient temperature increases sharply, making button mushroom and oyster mushroom farming difficult in this region. So with modern mushroom cultivation technology, it is now possible to do the mushroom seasonally in temporary mushroom houses, that is September to April for oyster, and by employing the controlled conditions in outdoor mushroom poly houses in hot regions. Ambient temperature is 20 to 20 degrees Celsius and humidity 85 to 90 degree, 90% is required for that. With the help of thermal insulation material in the roof and wall insulation, required environmental conditions could be maintained by using the supportive fan system and foggers. So thermal insulation is a versatile technology to maintain the temperature and humidity by preventing heat gain or loss to the mushroom cultivation model envelope. So thermal insulation is a generally construction material with low thermal conductivity, where thermal conductivity should be less than 0.1 watts per meter Kelvin. Calpoc fiber has a unique, why I am using the capoc fiber. Capoc fiber has a unique inherent properties of thermal insulation, and as well as it has a hollow structure. The recycled polyester, again, it is a cheap synthetic recycled polyester, which is obtained from the bulk. So these are some thermal conductivity terms, thermal resistance, and this is thermal conductivity, which is measured in lambda, and this is the coefficient of heat transmission value, which actually tells us about how much heat is transferred to the material. So aim of my study is that aim of my study is to develop the low cost lightweight thermal insulation material for the outward mushroom cultivation. Low cost because it should be affordable for the farmer, and in this study I have made attempt to evaluate the thermal insulation property of RPT and capoc multilayer non-woven manufactured by needle punch machine. These are the traditional seasonal mushroom houses. Here we can observe for reducing the temperature in, these are the seasonal mushroom houses actually. And here we can observe that they are using the agricultural material only. And here they have to continuously spray the water and like this for these mushroom houses to maintain the temperature as well as humidity. But what happens, mushroom is very much susceptible to the mold and biological attack, and due to that crop may get failure. So here these are the different mushroom houses we can observe. And here fibers I am using is recycled polyester and capoc. it has the density recycled. I want to use the lightweight, so this I have chosen the fiber of low density fiber, and these have the nominal thermal conductivity values are 0.15 to 0.24 for the recycle and CAPOC for 0.026 watts per meter Kelvin. And parameters affecting the thermal insulation properties are porosity, fiber orientation, and fiber fineness. Here I am focused on the porosity, and this we can vary with the help of fabric density and fiber density. So, and also the porosity is 1 minus packing factor, and packing factor is nothing but the fabric density by the fiber density. And this we can vary. If we vary this, phi will get vary, and porosity we can vary. So methodology I have used here that I have prepared the 4 samples of needle punch non-wound with varying density, punch density and GSM with machine parameters as punching stroke 300 strokes per minute, fabric advancement speed is 10 millimeters per minute, and I have prepared these 4 samples, 100% RPT single layer with 90 punches per centimeter square, 100% RPT with double layer with 90 punches per centimeter square, 100% RPT with single layer with 20 punches, and RPT plus CAPOC multi-layer. Here I have made the RPT layer first on the needle punch machine. Then I have made the CAPOC layer, and then I have punched it in on the needle punch unit with 20 punches per centimeter. These are the samples actually. This is 100% RPT of single layer. This is 100% RPT with double layer, and this is the low GSM with 20 needles per centimeter square. So characterization needs to products to be need for thermal conductivity, GSM thickness, and biological resistance. So these are the initial fibers which I have chosen. These are the testing results for that, and these are the thermal conductivity. And samples which I have prepared, these are 100% RPT. Sample composition is the only RPT. Number of layers I have chosen is single only, 9 punches 90, and nominal GSM was 217 GSM actually came, and the thermal conductivity I have it is 0.432, but the targeted value is 0.01 to 0.02 watts per meter Kelvin. So this is the targeted value. So this sample is not happened properly. Then another sample I have made this RPT again, and I have made these 2 different layers, and again with the same punch density I have used, and GSM was the 570, and here the thermal conductivity is 0.29. Then third sample I have made again this again RPT, but here I am using the punch density is low as I am not getting the targeted value. So here again I have number of layers single only I have used, and here the thermal conductivity I have achieved 0.006 watts per meter Kelvin. And another sample I have then gone for the only I was initially I have tried with RPT only. After that I have chosen the RPT plus CAPOC layer. Here I have chosen 2 layers RPT up and down, and in that CAPOC was sandwich. So 60% RPT with 40% CAPOC I have used here, and these are the punch density I have chosen as 20 only, and GSM was 300, and this or the achieve is 0.09 watts per meter Kelvin. So these are the graphical representation. Here RPT1 is 0.43, RPT the second sample is 0.3, and third sample is 0.06, and fourth sample I have achieved here. So approximate cost comparison I have made with the commercial materials as this is with the thickness 50-25 mm. The cost is approximate 170 square per meter is there in commercially. And these are the aluminum thermal bubble insulation some farmers are using. Here also the cost is higher. And this thermocol also they are using as the thickness is very low 2 mm, but the cost is very high. That is 200 rupees per cost per square meter. So if we go for the RPT and CAPOC approximate, I have taken out the cost, it will be around 80 rupees per square meter. So conclusion is that, so in 100% RPT with 200 GSM and low punch density have shown the better thermal insulation property than the higher punch density. It is due to the higher bulk. Then RPT plus Kapok multilayer non-woven shows the lowest thermal insulation value, because here we are getting the air entrapped properly due to the multilayer, and highest thermal insulation value. This is due to the presence of hollow Kapok fibers as well as high bulk. And RPT with Kapok fibers needs to be tested. Now this is, I am on very initial study, sir. I have not gone through many samples. It is going on. So this I will be trying with the different blend ratios. Initially, I have tried only 60:40 ratio. Then I have to try it for the different blend ratios also. I have to optimize the blend ratio and thermal insulation values. The light needle punch non-woven with higher air density shows the better thermal insulation performance, possibly due to more entrapped air in the structure and high bulkiness. So the interaction effect of aerial density and punch density on the thermal resistance was also found significant. So RPT plus Kapok thermal insulation material can be used for thermal insulation of mushroom cultivation model, as it has comparable thermal insulation properties with commercial available insulation material like thermocol, polyurethane, foam, and aluminum. They have achieved the thermal insulation value that is thermal conductivity value at 0.04, 0.03. So we have to achieve that, and again we have to go for the critical thickness value. That first we have to achieve the thermal conductivity which is required minimum, and then we have to arrange the different layers of that material, and we have to find out the critical thickness, and we have to calculate the U% value, how much heat will get transferred from inside to outside or outside to inside, that is U%, that we actually need to calculate, and it should be actually U% should be as per standards, it should be below 2, 1.8 to 2. If it will be, then it can maintain the temperature difference as outside to inside as 10 degrees Celsius as per literature review. So these are my references. So thank you. Actually, sir, in my study, I have to go ahead. Initially, I am on a very initial stage, so I have made some samples. For preparing the multi Kapok layer, we are finding the difficulties because in the on the same card, that is roller card, I cannot go for the Kapoks. I have made the Kapok layer on the miniature card where the strip card was there. There I have made the layer and I sandwiched there. So Kapok, so competitive another fiber for the Kapok is the polypropylene. This also I will be tried in my study. So initially I have tried this RPT plus Kapok, and I have found the some satisfactory results for the thermal conductivity. So and it has the low cost and lightweight due to the Kapok density and the RPT. Thank you very much, sir.
Okay, thank you, Swati, for your interesting work on recycled polyester and Kapok-based non-ovens. It seems that Dr. Harun has a question. Dr. Harun?
Yes,
please
yes,
go ahead.
Professor, I'm here. Regarding your thermal conductivity test, like how did you do those tests?
So thermal conductivity test is done with the hot plate method, sir. That is the hot plate method.
Hot plate method.
Yeah.
Hot plate method, like you used Kawabata system?
Yes, sir. Kawabata system, that is constant heat flow method. With the help of water, they have maintained the constant temperature, and temperature difference was 10 degrees Celsius. But more tests I have to do with that different temperatures we require to measure the thermal conductivity. But this is initial study only, and facility was not available in Mumbai. I will go for that test also. That thermal conductivity I will have to test 10 degree, 40, 50, like this I will have to do.
Yeah, I understand. But can you go to the other slide where you compare the thermal conductivity of all the fibers? Next one. Yeah, this one. So the 100% RPET, yeah, and the Kapok one, you are showing thermal conductivity values of around 0.0009. It means you have already better than the best super insulator available in the market. Okay.
Yes,
I
sir.
think these two values are not correct. These two values are not correct. You have to reevaluate your samples in the proper method. So the thermal conductivity that you're showing is of the super insulator. It's even lower than what is actually available in the market, or even
But yes, sir. Actually, I am also
found as.
confused with that. But I have done this test with the Kawabata system, and that test was that the temperature of water they have maintained as constant, and constant heat flow method was there, sir. So
Yeah.
this I am confused that whether I should go for the another test or like that.
No,
So,
this value is not correct. Something somewhere has went wrong. Even the equipment might have been faulty. So you have achieved almost like you see the
aerogel.
traditional fibers that you have, almost lower, even lower than the aerogel, I would say.
Hmm.
Aerogel even cannot produce such low thermal conductivities in general.
Okay.
So this is not possible. So the values that you are showing is not correct. You might need to check with the mission, or you have to go for the other mission for checking this one.
Okay, sir. Sure.
Okay. The top values are agreeable. Means 0.4 is okay, 0.3 is okay, but still 0.0006 is is not correct. Not correct. These two values are not correct. You have to check it
I
again.
will do, sir. Reevaluate it.
Yeah. Okay. Thank you.
Okay. Thank you, sir.
Sir, can I have a small question?
Yes, sir. I am here only. You can have.
On which machine you have made this sample?
So needle punch non-hole Dilo machine, sir. Dilo
Okay.
non-hole machine.
At VGTI.
It is not in Vidya, it is in Sasmira, sir. Sasmira, Mumbai.
Okay, thank you.
Okay, so now it's time for the last presentation of the session. And the speaker is Bhumi Sharma from National Institute of Fashion Technology, Mumbai. And the topic is upcycling textile waste for food packaging using bio-based film and aluminum foil, a sustainable approach. Yeah, so over to Bhumi.
Swati, can you please stop sharing your slides?
Yeah, sir, are you able to see my screen?
Yeah, now we can see your screen. Yeah.
Yeah, so good morning, everyone. My name is Bhumi Sharma, and I am a student from Department of Textile Design, National Institute of Fashion Technology, Mumbai. So the topic that I have researched upon is called upcycling. Is based upon upcycling textile waste for food packaging using bio-based film and aluminum foil. So a sustainably approachable method. So before starting the topic, I have been researching about this topic from quite a few months. So it is still on prototyping stage. I have to conduct few more research and tests before like completing this, so that it is still on prototyping stage. So I will be starting with my oral presentation. So the objective, on starting with the objective of the research, which is to reuse the textile waste, which is considered to be the one of the biggest waste in today's world. It is estimated that around 8.5% of global textile waste is accumulated in India every year. So most of the textile waste being end up in disposal or either in landfilling. So according to the reports, it is estimated that only 30 to 45% of the textile waste in India is being reused or is being upcycled. And the rest of the textile waste is either disposed or either like they end up in landfilling. So since textiles are quite close to my heart, and I'm currently studying textile designing, so that is why I came up with the solution that how can we reuse these textile wastes to produce the packaging based products. So mainly the packaging products that I have focused upon is are sweets. So I will be starting with my work plan. So the main research is done to upcycle these textile wastes for food packaging products using biocompostable film and aluminum foil. So through this research, experimentation has been done to combine these wastes. And one such way to combine these wastes is by making them into value-added products for food packaging. So the raw materials that I have used in this are aluminum as a laminating material, aluminum foil. Since aluminum foil is used in food packaging quite a lot, as it has properties like as it acts as a barrier to light and oxygen and odors and flavors, it has properties like this. So that is why I have used aluminum foil, having a GSM of 27.6 gram per meter square and thickness of 10.5 micron. Then the second raw material that I have used is called biocompostable film. So this biocompostable film is basically derived from renewable organic sources such as cornstarch and sugarcane, and then these sugarcane is then renewable, then fermented into lactic acid, and this biocompostable polymer film is derived out of that. And the third raw material that I have used are the different waste materials that I have collected from my having different aerial densities, and I have collected from my nearby fabric stores and the tailoring shops and all. And how I have combined these, so I have used fusing machines, fusing machine which is widely used in a fashion industry, the fabric fusing machine, to combine textile waste with the aluminum foil and this biocompostable film. So for the sample preparation, in order to get the suitable structure for packaging material, preparation of different samples has been done with different fabrics and combining the fabrics with aluminum foil and biocompostable film. So basically, I have experimented a lot, like how I can prepare these samples, how I can combine them with the textile waste. So first, I have tried it with adhesive, but since adhesive are made out of organic compounds and it is not quite eco-friendly, so that is why I moved to sample preparation using fusing machines. So in order to get more accurate structure and more accurate structure with sturdiness, the sandwich structure. So how I have prepared the sample. The sandwich structure was created by using biocompostable film, such as film as a sealant between fabric and aluminum foil. So what I have done between the fabric and aluminum foil, I have used the biocompostable film as a sealant. So it is basically combined using a sandwich structure. So the resultant formation is then passed through the conveyor belt of the fusing machine, where the structure gets fused. So during this experiment, like I have tried to fuse the sandwich structure with different temperatures of the fusing machine, starting from 100 degrees Celsius to 120, 135, and approximately at 150 degrees Celsius, it got stuck. So it got stuck precisely. So so this is how I have prepared the samples, as you can see in the slides. So in the first image, you can see the raw materials that I have used. So I have used basically 7 to 8 fabric samples like jute, linen, cotton, and corduroy and all, and canvas. And I have combined these textile waste with aluminum foil and this biocompostable film. And in the figure 2, you can see how I have prepared the sample with the sandwiching structure using the fusing machine. Yeah, so so the testing has been done on the obtained samples to determine the most sturdy and compact structure that can be used for making the packaging products. So I have done these testing to know like how sturdy and compact the structures that I have gotten from the fusing machine. So it is found out that the GSM testing is done using the test method IS 1964-2001 to determine, and it is found out that before and after laminating the textile waste with the biocompostable film and aluminum foil, the fabric GSM is quite higher after combining them with biocompostable film and aluminum foil. So the mass per unit area of the fabric has been increased after fusing them with these materials. Next is flexural rigidity strength. So the standard test method ISO 6490197 has been followed to determine the bending strength and flexural rigidity of the obtained fabrics before and after combining them with aluminum foil and using bio-based film as a sealant. So for this, warpway and weftway rigidity strength of the fabrics has been determined. has been conducted. So these two tests I have conducted, and I have still need to conduct more tests in order to get the most sturdy structure. After that, I have followed the design process. So being a design student, this is the basic design
Bhumi,
process.
you need to finish it in next 3 minutes.
Okay,
Yeah,
okay.
you have 3 minutes remaining.
Yeah, so being a design student, I need to we generally follow these design process in the fashion industry. First, we research about the market and trend research, then color and print research, then selection of the final theme, and after that, I have developed structure and patterns for making these sweet packaging boxes. And then on that, I have done surface explorations like screen printing and embellishment. So these are the results and discussions. So after post-laminating process using the fusing machine, so these are the structures that I have got after combining the textile waste with biocompostable film and aluminum foil. So the most sturdy structure that I have gotten is of jute and canvas fabrics. And this is the machine that I have used to combine these fabrics.
Fiber without any treatment, since we use since our textiles very stiff, we apply starch after making
Coming to results of this session.
There is no need to apply any starch in a week made out of pineapple leaf fiber. So it was
Am I audible?
Produced white, lustrous, and fine silky fiber with strength. So the fiber
Yeah,
is
actually, I don't know if sound is coming from some other presentation also.
the final product that I have made, and I'm using here as only
Yeah, now Bhumi, now you can start again.
Sorry, apologies for that, sir. So the fusing conditions, so these are the fusing conditions according to different temperatures that I have got. So during the experiment, I tried to fuse the sandwich structure at different temperatures, and as I have told, at approximately 150 degrees Celsius, I got the most sturdy and compact structure in order to make the packaging boxes. And these are the GSM. This is the table that shows how the percentage change of the GSM before laminating the fabrics with biocompostable film and aluminum foil, and after laminating them. So this is the percentage change. And this is the table for determining the flexural rigidity strength. So significant changes can also be seen in characteristics like bending strength and flexural rigidity strength of different fabrics. So these are the different fabrics that I have used, and comparing the flexural rigidity strength before laminating of these fabrics and after laminating these fabrics with biocompostable film and aluminum foil. So it is found out that jute and cotton canvas is more compact and sturdy and most suitable for developing the final products. So that is why I've made these final products using the jute and cotton canvas fabrics. So this is the whole design plan that I have followed, that we in generally in fashion industry follow in order to make the packaging, in order to make the products. So I've done the market and trend research, then the theme board development and print board development. And this is the print and all the themes that is being done by myself only. So this is as you can see in the figure, this is the final product that I came up with, that how we can use these textile wastes and then combine. So the inner structure, as you can see, it is made up of aluminum foil, where we can store the food, where we can store the chocolate sweets and all of that, the food packaging storage. And outer structure will be of fabric, the textile waste. And over that, we can do screen printing, and we can do embellishment in order to make the product look more appealing. So the screen printing and embellishment technique also has been done by myself, and the print technique also, and the whole structure is being created by myself. So this is on the prototyping stage, as you can see. So this is just the prototype that I have made till now. So this is the conclusion. So post lamination, there is a significant rise you can see in the properties of laminated fabrics. like there is an increased GSM, and it is found out that jute and cotton canvas fabric have the most sturdy and compact structure. That is why I created my final product with that. And according to these properties, I have further researched, and then I have conducted the design process, and on the basis of that, I have made my final products. So in that way, I have conducted my research. Thank you.
Thank you very much, Bhumi. Is there any question from the audience? If anyone is having any question, please go ahead.
Hello.
So, yeah.
May I have a question, sir?
Yeah,
Ms.
please go ahead.
Bhumi, what is bio-based film? How you have prepared it?
So bio-based film is actually, as we see that plastics are not eco-friendly and that are not sustainable. So bio-based film is basically derived from the renewable organic sources, such as cornstarch and like sugarcane. And then these are fermented and made into lactic acid. And this lactic acid is turned into these bio-based films. So in comparison to plastics and other things which are like quite frequently used in the packaging today, I have made use of this bio-based film.
Okay.
Yeah.
So have you made it by your own or purchased from outside?
No, currently actually my faculty has developed also. So basically I did this research with the help of my faculty. So he developed this with his colleague, and basically I sourced it from him.
Okay, thank you.
Thank you.
Okay, thank you, Bhumi, for your presentation. So with that, I'll conclude the session 22. So we had 4 interesting presentations from Govardhana Rao, Chilukoti.
Sir, excuse me, sir.
Yeah.
Sir, we are from Vaishalini group, sir. We didn't present our presentation here, sir. We are waiting.
Okay. Okay, Pratibha, is there any more presentation in this session?
No, sir. There are 4 presentation only.
Yeah,
I guess she has presentation in another session. She is not here.
Okay, so you may please guide her, because someone is saying no, they are having some presentation. Okay.
Yes, sir. Yes, sir.
Yeah. So we had 4 interesting presentation in this session made by Dr. Govardhana Rao, Chilukoti, Dr. Ankita Srivastav, Swati Chaudhuri, and Bhumi Sharma. And there was some important discussions and questions in the session. So I hope all of you have enjoyed this session, and I congratulate all the authors for their interesting presentation. Thank you very much. So session is now over.
Thank you all the speakers for such a informative talk, and I would like to thank you, Professor Abhijit, for giving his time and handling the session so beautifully. Now the next session will start at 10:30 in 10 minutes. So let's join them. Thank you, everyone.
Thank you.
Excuse me, may I know where is the valedictory session is happening?